Welcome to Study Loop.
The research balloon that is given this problem is filled with helium and it is reaching great altitudes very rapidly. This means that there will be no time for any heat exchange and the thermodynamic process can be observed as an adiabatic process. So we have the volume and the temperature of the gas on the ground level given as V1, P1, and T, and the pressure at the higher altitude is also given in the problem as P2. So to find V2, or the volume at the higher altitude, we need to use the very common equation that is related to adiabatic processes. So this is equation 19.24 from the textbook. So this is P1 V1 gamma equals P2 V2 gamma. And for the ideal monoatomic gas, gamma equals 5/3, or in rational form, and in the decimal form it is 1.67. So we can say that then V2 on gamma is P1 over P2 V1 on gamma, and then we need to raise both sides to the inverse to 1 over gamma and obtain V2 equals P1 over P2 1 over gamma times V1, and then substitute in all values. So this will be equal to 1 over 1.9, and then we will inverse. This will be 3 over 5 times 2 times 10 to the third power meters cubed. When we put these values into a calculator, we obtain that V2 equals 2.13 times 10 to the third power meters cubed, and this is the answer for the part A of the problem. So for the part B of the problem, here we have to find the final temperature, the temperature T2. So we'll use the relationship that connects pressure, volume, and temperature with this final state pressure, volume, and temperature for the given adiabatic process. From here we can derive that T2 actually equals T1 P2 over P1 and then V2 over V1. Since we know all of the right-hand side terms and their values, we can then substitute that T2 equals 288.15 kelvins times the ratio 0.9 over 1, this is in atmospheres, and 2.13 over 2, this is in 10 to the third meters cubed, and the final dimensions will be in kelvins. So the final result is that T2 equals 276.2. This is going to be 0.2 kelvins. And when we convert from kelvins to Celsius, we obtain that this is going to be 3 degrees Celsius. So this is a very low temperature on the higher altitudes. For the part C of the problem, we need to find the work done in this whole adiabatic process, and we will use the equation 19.26 from the textbook to use the already derived version, which says that the work done in the adiabatic process, or any adiabatic process, is gamma minus 1 P1 V1 minus P2 V2. And from here we can directly substitute. the work done is equal to 1.067 times, and then here we have the pressure, substituting the pressure, 1.13 times 10 to the fifth power, and this is in pascals. Then we have 2 times 10 to the third power meters cubed minus 9.117 times 10 to the fourth power pascals, and then this will be multiplied with, I'm going to write it over here, 2.13 times 10 to the third power meters cubed, and close the brackets. Placing all of these values into a calculator and evaluating it numerically, we obtain that the final value for the work done is 1.25 times 10 to the 7th power joules. And notice one thing, delta U will equal negative work. So in that case, delta U will equal minus 1.25 times 10 to the 7th power joules. And this is the answer for the part C. So here we have solved the whole problem. I hope you find this helpful, and I hope to see you in another lesson.